Authentication HTTP provides an extensible framework for servers that allows them to protect their resources and allows clients to access them through authentication. Servers can protect one or more of their resources, with each resource being assigned to a logical partition known as a realm. Each realm can have its own authentication scheme, or method of authorization it supports. Upon receiving a request for accessing a protected resource, the server will return a response with a status 401 unauthorized or a status 403 forbidden. The response will also contain a www authenticate header containing a challenge, indicating that the client must authenticate to access the resource. The challenge is an extensible token that describes the authentication scheme and additional authentication parameters. For example, the challenge for accessing a protected contacts resource that specifies the use of the HTTP basic authentication scheme is basic realm equals contacts. To explore how this challenge/response mechanism works in more detail, see Appendix. Authentication schemes. In the previous section we learned about the framework for authentication. RFC 2617 then defines two concrete authentication mechanisms. Basic. In this scheme, credentials are sent as a base 64 encoded username and password separated by a colon in clear text. Basic auth is conventionally combined with TLS. HTTPS due to its inherent unsecure nature, thus, its advantage is that it is extremely easy to implement and access, including from browser clients, which makes it an attractive choice for many API authors. Digest. In Digest, the user's credentials are sent in clear text. Digest addresses this problem by using a checksum MAC that the client sends, which the server can use to validate the credentials. However, this scheme has several security and performance disadvantages and is not often used. The following is an example of an HTTP basic challenge response after an attempt to access a protected resource. HTTP/1.1401 unauthorized. www authenticate basic realm equals web API book. As you can see, the server has returned a 401, including a www authenticate header indicating that the client must authenticate using HTTP basic. Get/resource HTTP/1.1. Authorization. Basic QWXBY2U6VGLI1HZ Tooljit Lig1 PC2GGT3 Zaza. The client then sends back the original request, including the authorization header, in order to access the protected resource. Additional authentication schemes. There are additional authentication schemes that have appeared since RFC 2617, including vendor-specific mechanisms. AWS authentication. This scheme, used for authenticating to Amazon Web Services S3, involves the client concatenating several parts of the request to form a string. The user then uses his AWS shared secret access key to calculate an HMAC hash message authentication code, which is used to sign the request. Azure Storage. Windows Azure offers several different schemes to access Windows Azure storage services, each of which involves using a shared key to sign the request. Hawk. This new scheme, authored by Aaron Hammer, provides a general-purpose shared key auth mechanism similar to AWS and Azure. The key is also never used directly in the requests, rather, it is used to calculate a MAC value that is included in the request. This prevents the key from being intercepted, such as in a man-in-the-middle MITM attack. OAuth 2.0. Using this framework allows a resource owner, the user, to delegate permission to a client to access a protected resource from a resource server on her behalf. An authentication server grants the client a limited use access token, which the client can then use to access the resource. The clear advantage here is that the user's credentials are never directly exchanged with the client application attempting to access the resource. You will learn more about HTTP authentication mechanisms and implementing them, including OAuth in chapters 15 and 16. Conclusion: in this chapter we've taken a broad brush approach at surveying the HTTP landscape. The concepts covered were not meant for completeness but rather to help you wade into the pool of HTTP and give you a basic foundation for your ASP.NET Web API development. You will notice we've included further references for each of the items discussed. These references will prove invaluable as you actually move forward with your Web API development, so keep them in your back pocket. On to APIs. Chapter 2: Web APIs. There's more to Web APIs than just returning a JSON payload. In the preceding chapter, we learned about the essential aspects of the web and HTTP, the application layer protocol that drives it. In this chapter, we'll talk about the evolution of Web APIs, cover various Web API related concepts, and discuss different styles and approaches for designing Web APIs. What is a Web API? A Web API is a programmatic interface to a system that is accessed via standard HTTP methods and headers. A Web API can be accessed by a variety of HTTP clients, including browsers and mobile devices. Web APIs can also benefit from the web infrastructure for concerns like caching and concurrency. What about SOAP web services? SOAP services are not web-friendly. They are not easily consumable from HTTP clients, such as browsers or tools like curl. A SOAP request has to be properly encoded in a SOAP message format. The client has to have access to a web service description LAN. Gauge WSDL file, which describes the actions available on the service, and also has to know how to construct the message. This means the semantics of how to interact with the system are tunneled over HTTP rather than being first class. Additionally, SOAP web services generally require all interactions to be via HTTP post, thus, the responses are also non-cacheable. Finally, SOAP services do not allow one to access HTTP headers, which severely limits clients from benefiting from features of HTTP like optimistic concurrency and content negotiation. Origins of Web APIs. In February 2000, Salesforce.com launched a new API that allowed customers to harness Salesforce capabilities directly within their applications. Later that same year in November, eBay launched a new API that allowed developers to build e-commerce applications leveraging eBay's infrastructure. What differentiated these APIs from SOAP APIs? The other emerging trend. These web APIs were targeting third-party consumers and designed in an HTTP-friendly way. The traditional APIs of the time had been mostly designed for system integration and were SOAP-based. These APIs utilized plain old XML as the message exchange format and plain old HTTP as the protocol. This allowed them to be used from a very broad set of clients, including simple web browsers. These were the first of many such web APIs to come. For the next few years after Salesforce and eBay took these first steps, similar APIs started to appear on the scene. In 2002, Amazon officially introduced Amazon Web Services, followed by Flickr launching its Flickr API in 2004. The Web API revolution begins in the summer of 2005. ProgrammableWeb.com launched. Its goal was to be a one-stop shop for everything API related. It included a directory of public APIs, both SOAP and non-SOAP, containing 32 APIs, which was considerable growth from 2002. Over the next few years, however, that number would explode. APIs would run the gamut from major players such as Facebook, Twitter, Google, LinkedIn, Microsoft, and Amazon to then small startups like YouTube and Foursquare. In November 2008, Programmable Web's directory was tracking 1,000 APIs. 4 years later, at the time of this writing, that number exceeds 7,000. API growth is accelerating, as just about a year ago the number was 4,000. In other words, it is clear that web APIs are here to stay. Paying attention to the web, the earliest web APIs weren't necessarily concerned with the underlying web architecture and its design constraints. This had ramifications such as the infamous Google Web Accelerator incident, which resulted in a loss of customer data and content. In recent years, however, with an exponential rise in third-party API consumers and in devices, this has changed. Organizations are finding they can no longer afford to ignore the web architecture in their API design, because doing so has negatively impacted their ability to scale. To support a growing set of clients, and to evolve their APIs without breaking existing consumers. The remainder of this chapter is a primer on web architecture and HTTP as they relate to building web APIs. It will give you a foundation that will allow you to leverage the power of the web as you begin to develop your own web APIs using ASP.NET Web API. Guidelines for web APIs. This section lists some guidelines for differentiating web APIs from other forms of APIs. In general, a key differentiator for web APIs is that they are browser-friendly. In addition, web APIs can be accessed from a range of clients including browsers at minimum. Support standard HTTP methods such as those mentioned in Table 1-to-1. T is not required for an API to use all of the methods, but at minimum it should support GET for retrieval of resources and POST for unsafe operations. Support browser-friendly formats. T. This means that they support formats that are easy for browsers and any other HTTP client to consume. A browser client can technically consume a SOAP message using its XML stack, but the format requires a large amount of SOAP-specific code to do it. F. Formats like XHTML, JSON, and form URL encoding are very easy to consume in a browser. Support browser-friendly authentication. T. This means that a browser client can authenticate with the server without requiring any special plugins or extensions. Domain-specific media types. In the previous chapter, we learned about the concept of media types. In addition to the general-purpose types we discussed, there are also domain-specific media types. T. HES types carry rich application-specific semantics and are useful in particular for web API development where there are rich system interactions rather than simple document transfer. vCard is a domain-specific media type that provides a standard way to electronically describe contact information. It is supported in many popular address book and email applications like Microsoft Outlook, Gmail, and Apple Mail. In Figure 2-to-1, you can see the same contact represented as a vCard. Figure 2-to-1. Contact vCard representation. When an email application sees a vCard, it knows right away that this is contact info. Machine and how to process it. If the same application were to get raw JSON, it has no way of knowing what it received until it parses the JSON. T. This is because the JSON media type does not define a standard way to say I am a contact. The format would have to be communicated out of band through documentation. A. Assuming that info machine was communicated, it would be application specific and not likely supported by other email applications. In the case of the vCard, however, it is a standard that is supported by many applications across different operating systems and form factors. We can mint new media types as applications evolve and new needs emerge by following the IANA registration process. T. This provides a distinct advantage because we can introduce new types in clients to consume them without affecting existing clients. As we saw in the previous chapter, clients express their media type preferences through content negotiation. Media type profiles. It makes a lot of sense for media types that are used by many different clients and servers to be registered with IANA. But what if a media type is not ubiquitous and specific to an application? How'll it be registered with IANA? Some say yes, but others are exploring lighter weight mechanisms, in particular for web APIs. Media type profiles allow servers to leverage existing media types like XML, JSON, etc., and provide additional information that has the application-specific semantics. The profile link relation allows servers to return a profile link in an HTTP response. A link is an element that contains a minimum of two pieces of information: a rel or relation that describes the link, and a URI. In the case of a profile, the rel will be profile. It is not necessary for the URI to actually be dereferenceable, meaning you can access the resource, though in many cases it will point to a document. The challenge with using profiles today is that many media types do not currently support a way to express links, so clients would not be expected to recognize the profile even if it were in the content. For example, JSON is a very popular format used by web APIs, but it does not support links. Fortunately, there is a pre-established link header that can be used in any HTTP response to pass a profile. Using the earlier contact example, we can return this header to tell the client this is not just any old JSON, it's JSON for working with example.com's contact management SYS. TEM. If the client opens their browser to the URI of the link, they can get a document that describes the payload. This document can be in any format, such as the emerging application level profile semantics ALPS data format, which is designed specifically for this purpose. http://1.1200 OK content type application/JSON, charset equals UTF-8 link, rel equals profile. Date Friday, December 21, 2012 064725 GMT. Content length 183. Contact ID 1. Name Glenn Block. Address 1 Microsoft Way. City Redmond. State WA. Zip 98052. Email blockmicrosoft.com. Twitter block. Self. /contacts/1. Multiple representations. A single resource can have multiple representations, each with a different media